Hello students, I hope you are all are doing good. So the topic that we are going to discuss today is current electricity NCRT section 3.4 to 3.5. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. Okay, the topics that we are going to discuss today is NCRT section 3.4, that is Ohm's law, and NCRT section 3.5, that is drift of electron and the origin of resistivity. So our first topic, Ohm's law. So Ohm, this law is based on the name of scientist. So Ohm discovered a basic law about current flow in 1828. So scientist Ohm discovered a basic law in 1828 before understanding of the physical mechanism of current flow. Okay, we got to know after so much time that flow of current is due to the flow of electrons. It was assumed that flow of current is due to flow of positive charges, but after some time it was cleared that current flow is due to flow of electrons. Okay, so that mechanism of current flow, before that Ohm discovered a law that is known as Ohm's law. So what is that law? If the physical conditions such as temperature and pressure, okay, and temperature in this specific case of a conductor remain same, then the current I flowing through the conductor is directly proportional to the potential difference V across its end. Okay, so if the physical conditions remain constant, okay, we don't want any temperature variation or pressure variations, okay, then current I flowing through the conductor is directly proportional to potential difference across its ends. Or we can say potential difference across its ends is directly proportional to the current flowing through that conductor if the environmental conditions or physical condition like temperature and pressure remains constant. Okay, if temperature will increase, then temperature of the connecting wires and resistor will increase, then there will be change in the resistance. Okay, so this proportionality will disturb. That proportionality of potential difference with current will disturb. Okay, so how resistance is changing with temperature, we will going to discuss in this chapter in the later topics. Okay, so we have to maintain the physical conditions as constant. Okay, so mathematically it can be represented as potential difference is proportional to current through the conductor. Okay, and after removing this proportionality constant, it will come at, this is constant of proportionality. After removing this proportionality constant, this is constant of proportionality known as resistance of the conductor, where R is the conductor's resistance acting as a constant here measured in ohm. So this is the SI unit of resistance, ohm, and it is represented as this, and it is constant of proportionality here, and this R depends on only the material property and dimensions of the conductor. Okay, it doesn't depend upon potential difference and current flowing through the conductor. So this resistance R only depends on material, the material of the conductor and dimensions of the conductor. Means if the material is copper, or we can say silver or aluminium, it will depend on material. Also it will depend on the dimensions of conductor, that its length, its radius if it is cylindrical, its width if it's rectangular. Okay, so this will depend on dimensions. Okay, we will we are going to prove this also in our upcoming slides, and it is also dependent upon material. but it doesn't depend upon potential difference and current in most of the time. Okay. So what is the objective of learning Ohm's law here? To understand the dependence of resistance on length and cross-sectional area, that we are going to discuss. That what is the dependence of resistance on the dimensions of conductor, and what dimensions? Length and cross-sectional area. Okay. Consider a conductor as a slab with length L and cross-sectional area A. So this is a rectangular slab having length L and this cross-sectional area A. Okay, so these are B and C case. We will discuss these two cases one by one. Initially, we have only one slab having length L and cross-sectional area is A. So figure 3.2 illustrating the relation R equal to rho L by A. This relation we are going to derive. Okay, R equal to rho L upon A. What is rho? We will discuss. And this is length, this is area of cross section. So this relation we are going to get after doing all these things for a rectangular slab of length L and cross sectional area A. Okay, so this figure is illustrating the relation, this relation. Okay, again this diagram. Now, when two identical slabs are placed side by side, length 2L, this case, they are talking about this B case now. Okay, when two identical slabs are placed side by side like this, one slab, then another slab. Okay, side by side such that their length is now 2L, L plus L. The current remains same through the both slabs. Why current remains same? Because in this slab, when we took this single slab, number of electrons in this slab is constant. Okay, when we then current through this slab will be I. Now these both slabs are this slab are placed side by side. Okay, so number of charges in this slab and in this slab is same because they are identical. So current flow through both the slab will be equal to I. So current flow will not change. Current remains same throughout the both slabs. But what is changing here? Length. Length becomes now 2L. Area of cross section remains same also. Area of cross section is A for this slab and for this slab also. Okay. So area of cross section and current through these both slabs will be same. But lengths become double. Okay, with potential difference V across each slab. Okay, now see, potential difference across this one slab is V. Potential difference across this one slab is V. Now we are connecting these by side. So potential difference across this slab is V. Potential difference across this another slab which is placed side by side is also V. Okay, so potential difference across one slab is V. Okay, now we have placed it side by side. So potential difference across both these slides is now 2V. V across this slab and V across this slab. So total potential difference across both these slabs is 2V. Got it? So with potential difference V across each slab, the combination's total potential difference is 2V. The combination's resistance is now we are going to find combination's resistance RC, the combination of this B diagram. So RC is equal to 2V upon I. Okay, now we know that for this single slab, resistance is V upon I. V is the potential difference across its ends and I is the current flowing through that slab. So this is R for one slab. Now resistance for this combination RC will be equal to, now potential difference across both its ends is 2V. okay, upon I. Current flowing is I. So now V by I will become R, this R, and this is 2. Now resistance of combination is doubled. Okay, when we double the length, resistance of combination also doubled. When we increase the length, resistance of the combination also increased. What this thing mean? That resistance is directly proportional to length. Means if length is increasing, resistance is also increasing. Okay. So the resistance is proportional to length, like this. So if length is increasing, this resistance will also increase. If length become double, this resistance will also become double. Again this diagram. Okay, now we will see the dependence of resistance on the cross-sectional area. We have seen the dependence of resistance on length. It is directly proportional to length. Now we will see the dependence of resistance on the cross-sectional area. So like this. Now we are dividing this slab into two parts like this, such that area of cross-section of both the slab becomes half. Okay, A by 2, A by 2. Okay, we are cutting or we are dividing this slab along its length, such that there is A by 2 area of cross section of upper slab and same A by 2 area of cross section for lower slab, but length remains same. Length is not changing. Okay, when the slab is cut lengthwise, into two parts such that each with area A by 2, the current divides equally I by 2. Why current is dividing now? I have already mentioned that it is if this is a whole slab. Okay, so number of current, suppose there are n number of electrons present in this, or n number of charge carriers or mobile charges are present in it. Okay, when we cut this slab, now it becomes half. So number of charge carriers or number of electrons in one slab after cutting in upper slab will be equal to n by 2, because it becomes half. After cutting it became half. So now number of charge carriers reduced to also half. Okay, if number of charge carrier reduced to half, mean charge in between this upper conductor becomes half. So since current is proportional to the charge, so current will also becomes half. Okay, current is due to the electrons, moving electrons. If number of electrons is reducing to half, then current is also reducing to half. Got it? So current divides I by 2, but the potential difference across its end remains V, because we are cutting it along length. So length is same, potential difference that we are applying across its both ends is V after cutting or before cutting, but current is becoming half. Length remains same, area of cross section is also becoming half. Okay, the resistance R1 of each half slab. Now R1 resistance is resistance of each half slab. Either it is upper half, either it is lower half, because they are cut into equal parts. So any of the half slab, R1 resistance is given by V upon I by 2. So 2 will go in numerator. So we know that for whole slab R equal to V upon I. Okay, so V upon I becomes R for whole slab. Now resistance of half slab is becoming 2 times the resistance for full slab. Now what can we interpret from this result? We have reduced the area of cross section to half and resistance is becoming double. Okay, so now we can infer from this result that if area of cross section is decreasing, resistance is still increasing. Okay, if area of cross section is becoming half, resistance is becoming double. This means resistance is also proportional to A, but which proportional, direct or inverse? it is inversely proportional to A. Means if one quantity is increasing, other is decreasing. Okay. Therefore, resistance is inversely proportional to the cross-sectional area. Okay. And it can be shown like that. R proportional to 1 by A. If A is increasing, then this resistance will decrease. And if A is decreasing, like we have reduced this A to half, then resistance will increase and become double. Now, combining these proportionalities. Firstly, we discussed dependence of resistance on length, and we came to know R is directly proportional to L. Now, we discuss dependence of resistance on cross-sectional area, R proportional to 1 by A. Okay, now combining these both the proportionalities, we will get R proportional to L by A. R is directly proportional to L, R is inversely proportional to A. Okay, now we have to remove this proportionality constant also. So what we will do? Removing this proportionality constant, this rho will appear as a constant of proportionality. What is this rho? Rho is resistivity of the conductor. Okay, and it is material property. It doesn't depend upon dimensions of the conductor, only depends upon material of the conductor, where rho is the material's resistivity. Okay, resistance depends upon both material properties and dimensions, but this resistivity depends upon only upon material property. It is material property. Resistivity is material property. It is different for copper, it is different for aluminium, it is different for silver, but it doesn't depend upon dimensions of the conductor. Okay, so now R, this resistance is clearly depending upon material property, this rho, and the dimensions, length and area of cross section. Okay, so this is the dependence of resistance on length and cross sectional area. Got it? Now, what we are going to do, what is our objective now? Derivation of Ohm's law in vector form. Okay, we have seen the normal form, which is V proportional to I and V equal to IR. Okay, this is a common form of Ohm's law. Now in vector form, what is Ohm's law? Ohm's law can be rewritten as V equal to IR. This is simple form. Now this R can be written as now rho L by A, as we have derived the relation. R is rho L by A. So V becomes I rho L by A. Okay. Now current density. What is current density? We have already discussed it in electrostatic chapter also. Okay. So current density J is current per unit area. Okay. Which is I upon A. So current density J, which is I upon A, for uniform electric field E in conductor length L, V equal to EL. Okay, we also know V equal to EL. How? If this is a conductor, cylindrical conductor, okay, so across it both the ends, we have maintained the potential difference of V with some external source. Okay, and this is electric field. Suppose this is electric field we have applied in this direction. Okay, and this is length of conductor is L. Okay, so V is equal to EL. How? According to the relation of electric field and potential difference, which is E equal to minus dV by dr, and magnitude of E is dV by dr. Potential difference upon the displacement, the separation. So now the separation between its both ends is L, length of the conductor, and V is the potential difference and E is the electric field. So we can write V equal to EL. Okay, so V equal to EL. So now putting this V equal to EL here, and this current density J, I upon A will be converted into J. So now equation will be EL V. V equal to EL equal to I upon A is J, current density, rho L. Okay, so now L will cancel out from both sides. So it will become E equal to J rho. E equal to J rho. Rho here is not density. Rho here is resistivity of the material. Okay, so E equal to capital E electric field equal to current density into resistivity. Okay, so now Ohm's law in vector form. Now we can represent the Ohm's law in vector form. So electric field is vector and this current density is also vector. So we can represent it is in vector form. So E vector, this bold letters mean vector quantity. Okay, so bold letters means vector quantity. So this electric field vector equal to this current density vector into rho, resistivity. So this is the vector form of Ohm's law. Also we can write it as J equal to sigma E. Now how rho became sigma? Rho will go there in denominator below E, and 1 by rho is equal to sigma. Sigma is not surface charge density here. Sigma here is conductivity. Okay, in electrostatics we used sigma as surface charge density, but in this chapter current electricity, sigma is 1 by rho. Sigma is equal to 1 by rho. When this rho will go there below this E, so it will become 1 by rho. 1 by rho is sigma, which is called conductivity. It is also material property like resistivity. Okay, so these two are the vector forms of Ohm's law. Okay, so these results also be used in our upcoming derivation. This result J equal to sigma E. Okay, we will also derive for this sigma, the value for this sigma. Okay, in the upcoming slides. Now our next topic, drift of electrons and the origin of resistivity. Okay, what is the objective to learn this topic? To study how electrons in a conductor behave with and without an electric field. Okay, so how electrons will behave in conductor. There are number of electrons, how they will behave with or without an electric field. Okay, leading to derivation of Ohm's law, and we will derive the Ohm's law. Now we have seen the simple form of Ohm's law, vector form of Ohm's law. Now we will derive it. Okay, and find the value of sigma and J also. Okay, so this is our objective here. Okay, so suppose this is the path of an electron in the conductor. Electron is moving from A and reaching B and B dash through two paths. One path is this blue line path and other path is this dotted line. Okay, so how this dotted line path is different from blue line, we will discuss. Okay, now the electron motion is random and these corners are points of collision. Means here collision happened. When electron is moving in the conductor, it is colliding with the stationary ions, bound ions. Okay, ions that are containing nucleus and bound electrons. Okay, so electron is colliding with that ions and with other electrons, and after collision its path is changing. So suppose it is moving from A, after reaching this one point it will collide with another ion and its path diverted. Now it will reach point 2. Now here again collision happened and it will deviate through its path. It will reach this 3 point. Again collision happened and so on. And after going through so many collisions, it will reach at B point. Okay. So figure 3.3, what is it showing? A schematic picture of an electron moving from a point A to another point B through repeated collisions and straight line travel between the collisions. Okay, so between two collisions, electron will travel through straight line, not through that type of path. Okay, between two collision, it will travel like straight line. Okay, so a schematic picture electron moving from A point to B point through repeated collisions and straight line travel between collisions, full lines, that blue lines. And this blue line path of electron is due to the absence of electric field. When electric field is not there, this blue line path is for electron when electric field is not there. If an electric field is applied, now if an electric field is applied, the electron ends up at the point B dash. Then electron will follow this dotted path. If electric field will apply like this as mentioned, electric field in the direction left side. In left, electric field is applied in the left side direction. Okay, so when electric field is applied, the path of this electron is dotted lines and it will reach B dash point. Okay, a slight drift in the direction opposite to the electric field is visible. Now you can see that this B dash on this dotted path is slightly drifted from this blue path. In which direction? In the direction opposite to the electric field. It is drifted in that direction opposite to the electric field. We know that electron feels force, experience force in the direction opposite to the electric field. Okay, so here now electric field is applied, so path of electron will be deviated and drifted towards the right side in the opposite direction of the electric field. Okay, so now we are using this drift term. What is this drift? I have already discussed in briefly in previous lectures that drift is electron. We cannot say that electron move, electron drift, because when electron start moving, it will collide with another ion, then it will lose its energy, most of its energy, then it will again accelerate in the electric field and gain some velocity. After some time again it will collide. So these small movements, small distances covered in between two collisions, and the velocity gained between two collisions, and the path due to which electron is moving like this is called drift of electron, not movement of electron. More appropriate term is used, drift. Without an electric field, the electrons collide with heavy fixed ions but maintain the same speed in random directions. Okay, so if electric field is absent in the region, electron collide with heavy fixed ions but maintain the same speed in random direction. So same amount of electron will move in all the directions. Okay, their motion is random in the absence of electric field, but they will maintain a same speed in a random direction. Means some electrons are moving upward, some are moving downward, some are moving forward, some are moving backward. Okay, so their direction is completely random. For n electrons, their average velocity is 0. Okay, if there are n electrons in the conductor and there is no electric field present. Okay, so for n electrons, what will happen? Their average velocity is 0. Means number of electrons that are moving in forward direction and number of electrons that are moving in backward direction are same. Number of electrons moving in upward direction and number of electrons that are moving in downward direction is same. So electrons are moving in random directions. So this can be represented as like this: summation I equal to 1 to n. This means Vi, this is the velocity of one electron, and 1 to n means velocity of all the electrons, means summation. This means velocity of one electron and I is varying from 1 to n. So summation of sum of all the velocities of electrons divided by the total number of electrons. This is the average velocity. So average velocity will be equal to 0. Okay. Okay, when an electric field is applied, electrons experience acceleration. Okay, now when electric field is applied, then electron will experience a force. In which direction? In direction opposite to the electric field. Okay, so if the electron is experiencing a force, then electron will experience the acceleration also. Okay, so what is the value of this acceleration? Minus E, capital E upon m. How this thing came, I will explain. So if we know that force experienced by the electron will be, or force experienced by any charged particle is equal to Q into E. Okay, what is Q here? For electron, minus E, and E, capital E is the electric field. Okay, this F can be represented as mass of electron into acceleration of electron, and this acceleration will be then represented by minus E, capital E upon m. For any electron after time t dash from its last collision, its velocity becomes, okay, suppose one electron is going like this and their collision happened at point 1. Collision happened. After some time it is moving in this path, and if at this point 1 collision happened, and after ti time after from its last collision, it has covered some distance after this first collision. Okay, if electron has suffered one collision, okay, at point 1, so after that collision it has discovered some distance. Okay, and after time ti from its last collision, that is this collision, its velocity becomes, okay, when this electron is at point 1, collision happened, and just after the collision there is some velocity, v, small vi, for this electron, which is random in any direction. We can't determine the direction of velocity after collision. Okay, but in the presence of electric field, after some time it will experience force in the direction opposite to the electric field. So then direction of velocity will change. Okay, so it will follow the specific path, that is this, under the influence of electric field. So after time ti, what is the velocity now under the acceleration of electrostatic force? Okay, so like this, capital Vi is equal to small vi plus minus E, capital E upon m ti. Okay, so what is this? This is first equation of motion, v equal to u plus at. Okay, so what is v? Final velocity after its last collision. Its last collision happened at point 1. So after its last collision and after ti time, what is the velocity now? And small vi is the initial velocity, which is velocity just after the collision. Just after the collision, what is the velocity? Which is completely random. And this is the acceleration of electron, minus E, capital E by m, into what is the time elapsed. So after ti time from the last collision. Got it? Now average time between successive collisions lead to the drift velocity. Okay, now we are not taking specific times, we are taking average time between successive collision. Okay, if this is an electron and one collision is happening here, second collision is happening there, third collision is happening there, and fourth collision, after it reaches here, 1 2 3, and this is fourth collision, and now it has reached here. Okay, so you can see this is the path covered in between these two collisions, first and 2. This is the path covered between 2 and 3. Okay, now you can see the path covered in between 1 and 2 collision will be more than the path covered between 2 and 3 third collision. Okay, so also time taken, time consumed, or time between the two collisions, first collision and second collision, is the relaxation time. Time between two successive collision is known as relaxation time. Okay, average time. So this is the time taken between these two collisions, and this is the time taken between suppose T1 is the time taken between first and second collision, and T2 is the time taken between the two collisions 2 and 3. Okay, so you can clearly see the distance covered in the between the second and third collision is less, so time T2 will be less than T1. Okay, so similarly for every successive collision, the time between two collision will be different, not always same. Okay, so time between successive collision will be different for different collisions. Okay, so we are taking average time, not a specific time. We are taking average of all the time between the successive collisions through which electron goes. Okay, suppose electron has gone through 100 collisions. The time between every two collision is different, so we cannot take one time arbitrary. Okay, so we can take the average time between. We will take average of all the times between two successive collisions, and we will take the average, which is also known as relaxation time. Average time between successive collision, also known as relaxation time, and it is represented by tau sign, that is used for torque. Okay, leads to the drift velocity. Okay, so now drift velocity can be given, and this vi is greater than this initial velocity. Okay, or this vi can be greater or lesser. Okay, it is not based on the it is based on the distance traveled or relaxation time. Okay, if electron is traveling more distance after first collision between two successive collision, it is covering more distance, so it will accelerate through more time, so this velocity will be greater than this. Okay, if it is covering very small time between two successive collisions, then it will not get enough time to get accelerate, so it will get small velocity. So either it can be less or larger than small vi. It cannot be determined completely. Okay, we will take average of velocities, we will not take the specific velocities. So this vd, drift velocity, what is this drift velocity? It is the average of all this capital vi's. Okay, this drift velocity, average of all the capital vi's and average of this small vi's minus e capital E upon m, and average of all the times between two successive collisions. Okay, now there are number of electrons. This thing is for one electron. Okay, we cannot take one electron and derive the derivation. Okay, it will be incorrect for other electrons. So we will take the average thing, average of all the velocities. So this is average of this one, capital Vi average is the average of all the velocities of the electrons after some ti time from their last collision. We will take average of all the velocities, and this small Vi average will be 0. Why 0? Because after collision the motion of the electron is random. Just after collision, motion of the electron is random. It will go in any direction, random direction. Okay, after some time when it will feel electric field, then its direction will become specific, but just after the collision it will go in any random direction. So this small vi for all the electrons is random, so its average will be 0. Okay, and this ti, I have already explained that average time between time between two successive collision is different for every collision, so we will take average of this only. Got it? So this small vi average is 0 minus e capital E upon m, and this ti average is tau. So now drift velocity is given by minus e capital E upon m into tau. Okay, this is given. Now this is the another thing. What is this? This is a conductor, and this is the direction of electric field. Electrons will move in this direction. Okay, and this is the length of the conductor, which is given by drift velocity into time consumed, velocity into time. So electron will take delta t time from going from this left section to this right section. They will consume delta t time, and their velocity, drift velocity is vd. So length of the conductor, or this delta x distance traveled, is given by vd into delta t. Got it? So what is this figure representing? Current in a metallic conductor. The magnitude of current density in a metal is the magnitude of charge contained in a cylinder of unit area and length Vd. The drift causes charge transport across the areas perpendicular to E. For area, the current is given by. Okay, this drift of electron cause the transport of charges across the area that is perpendicular to E. So this is area of cross section that is perpendicular to this electric field. So charges will start drifting across this perpendicular area in the direction opposite to the electric field, because they are negative charged particles, electrons. For area A, the current is given by I delta T NEA VDT. How this thing came, I will explain. Okay, so what is this N? N is the number density, also known as number of particles per unit volume. Okay, so this small n is number of charged particles, number of electrons present in this conductor upon the volume of this conductor. Means it can be represented as number of electrons in the conductor upon the volume of the conductor. Okay, in left hand side, what is given? Current into delta T. What is this? Charge. Okay, charge flowing through that area A. I into delta T. We know that I is equal to Q by delta T. So I into delta T will be Q. Charge flowing through this area A. So this is charge, left hand side. We also want right hand side as charge. So what is this? Small n, number of electrons per unit volume, into E. What is E? E is the charge on one electron. So charge on one electron, we will get the charge in the right hand side if we multiply this small n with volume. If we multiply this small n with volume, it will become, if we multiply this with volume on both sides, it will become, this volume and volume will get cancelled. It will become n, number of particles, number of all the charges, into charge on one electron. It will give us the charge on the right hand side also. Okay, so what we have to do, what is this Vd delta T? It is given length of the conductor. And what is this A? Area of cross section. So collectively A Vd delta T is volume of the conductor, and this small n is n by V, and this E is amount of charge on one electron. So what it became? V and V will get cancelled out, volume and volume will get cancelled out. So number of charge particle into charge on one particle. So it is total charge. So it is total charge in the circuit. Got it? So total charge in the conductor. So left hand side is also that thing, I into delta T, total charge in the conductor. I hope you got it. Okay. Now I delta T. Now put this, the value of Vd. What is the value? What was the value of Vd? Is minus E, capital E upon m tau. So we are taking magnitude of this Vd, drift velocity. So we will take the positive sign, magnitude. Okay, put this value in this. So n is already present. Okay, E is already present. One E is from this, E square. A is already present upon m from this. Tau, n is already present, delta T and this E. Now we are taking, E is a vector quantity, so we are taking the magnitude of E. This mode is magnitude of E. And why we are taking this positive sign? Since this E, charge on electron, is negative, why we are taking this negative sign? positive sign here. Why we are not taking negative sign? Because direction of current is opposite to the motion of electrons. We assumed earlier in our conventional direction that flow of current is opposite to the flow of electrons, and it was earlier considered that flow of current is due to flow of positive charges. That's why we are taking current here, so that's we are taking here positive sign. Okay, got it? So this is Vd. After putting the value of Vd, that is magnitude of Vd, ignoring the negative sign, EEM tau. So putting the value of Vd here, you will get this thing. Okay, and why you are getting this positive sign here? Because current is considered in the opposite direction of electrons, flow of electron. That's why we are taking positive sign here. Okay, now current density relates to current as, so current density is related with current as I equal to JA. J is vector quantity, we are taking magnitude for now. Okay, we will take vector as in our next part. So I is equal to mod of J into A. So current density is given by I upon A. So current is given by J into A. So comparing it with 3.19, we will get J as NE square by M tau magnitude of E. This 3.20 and compare it with 3.19. Okay, you will get this value of J. Value of J is NE square upon M tau and magnitude of E, because we are dealing with magnitudes. And in vector form, we will remove this magnitude sign and we will get the vector portion. J equal to NE square upon M tau E. Okay, so what is this value now? We know that J is equal to sigma E. That was the vector form of J equal to sigma E. That was the vector form for Ohm's law. So sigma from here is this term, NE square tau by M. So derivation shows Ohm's law with conductivity sigma equal to NE square by M tau. Okay, assuming that constant tau and N. So relaxation time for a conductor is constant. Average time between the successive collision for a given conductor for a given material is constant. Also number density of electron means number of electrons per unit volume of the conductor for a given material is also constant. And this sigma, this conductivity is independent of the electric field. So this is the relation of sigma, and we can also write this sigma as 1 by rho, and we will get the value of rho also. Okay, so this is the derivation of Ohm's law, and we have also determined the value of current density and sigma and rho. Okay, so thank you. I hope you enjoyed and understood the lecture well.